Hey, John here. Let's look at the 8 queens problem. First, let's try to understand what the problem really is, okay? Let's say you have a checkerboard or a chessboard. We don't care about the black and white squares in this particular scenario. So it's an 8 by 8 grid, all right? These are queen chess pieces, all right? I don't happen to have 8 of them, so let's just use these. So if you place a queen on a chessboard, what we know is the queen is free to move vertically and horizontally as far as she wants. She can also move on an angle 45 degrees as far as she wants, okay? That's any one of the 8 directions, okay? Now, if I put 2 queens on a chessboard, let's put them both here, then these are open to risk. They're not safe from attack, right? Because queen can move up, this one could move down, all right? If I put it over here, these 2 queens cannot attack each other because you cannot get there in one move, I should say. They cannot attack each other because all the 45s and so on, they can't get there, okay? So these 2 are safe from attack, we say, all right? If I place a 3rd queen on the board, say like right here, it's safe from this one, but not from this one here because of the angle, right? But if I put it here, it's safe from both, right? I can't get it here, I can't get there, not vertical, not horizontal, all right? So what happens if I put 8 of them on the board? Is it even possible to put 8 on the board without having them open to attack from each other? Well, it turns out there are 92 scenarios where you can do that. And we're going to write a program that finds and prints out the board matrix of each of those cases. So in order to put 8 on one chessboard, we know going into this that they can't be in the same columns. All right. They also can't be in the same rows. So we can reduce the number of things we need to check by a massive quantity by simply saying we know a priori that only one queen will be on each one of these rows. Okay. So I'm going to line them all up like this. Okay. We also know that there will only be one in each column. But if we look at a specific algorithm, it turns out we can't take advantage of both of those pieces of knowledge at the same time, at least not conveniently so. It's real easy to think of this in a kind of a brute force kind of method. As long as we use this one optimization, we can write a program that will ultimately finish running in our lifetimes. Otherwise, we have a lot more things to check, right? Okay, so here's how we can do this. Let's just place one queen on the first row and in the first column. Then we can simply ask, is it open to attack from anywhere? And obviously the answer is no. There's only one queen on the board. The answer is no. Let's try putting one on the second column. Well, first thing we could do is try to put it in the first column. No, it's open to attack. How about the second column? Open to attack, right? Third column. Nope, that's safe right there. All right, what about the next one? Well, let's try the first one. Open to attack. How about here? No, it's got an angle attack there. Now it's got an angle attack from this one here, angle attack from there, and we're looking good here. It's safe, okay? How about this one? Open to vertical attack. That looks pretty good. Not open to attack anyway. This one's safe. All of them are safe, in other words, okay? Now notice, what are we doing? We're only working from the top down, so when we look at whether to assess an attack, I'm not looking down here. It's just pointless. There's nothing down there. It can't be down there, okay? This is what saves us some time. We're only going to look up because there's nothing else yet placed below it. So what about the next row? We come along, open to attack, open to attack, open to attack. What about here? That looks like it's safe, all right? That looks great. So what about the next row? Open to attack, open to attack, open to attack. Again, these are all easy, obvious attacks from the vertical there. What about here? This one looks like he's open to attack on an angle. What about here? He's open to attack on that angle there. What about here? He's open to attack on that angle there. All right, so now we've failed. All right, what do? We do what we call backtracking. We've checked every column for this row, and this can't be done. So we take it off the board. And we go back and reassess this guy up here, right? Well, it turns out we already know that we've checked all of these spaces over there with this configuration that's up above already. So we know none of these are good. We already checked them. So move on. How about here? Open to attack. Here. Open to attack. How about here? Looks good. Looks good. Open to attack. How about over here? Looks good. looks good that way, and there's nothing to attack them there. So this also would work. There's two possible ways to deal with this configuration when you're on this row. And then reassess. And you have to start at the beginning. Once you've touched anything up here, we have to reassess this entire row, right? So he's open to attack, open to attack, open to attack. He's got an angle attack there, vertical attack, looks like attack there, and then that's attack, and that's... So this is not safe, all right? Well, this one was a candidate. It's not safe either, and there's nothing else to check. Take him off the board. What do we do now? We backtrack up to here. We know that we've already checked this other one, and we haven't touched anything north of this guy yet. Moving forward, try again. No good. No good. No good. No good. And that's okay. Come back down here and start over. Open to attack. This okay. We got angle there. We got angle there. That's a safe place for this guy. All right. Try this one. He's vertical attack, vertical attack, vertical attack. We've got an angle that looks clear. That's clear. And that's clear. So this is a safe place for that one. Come down to this row. First one. Vertical attack, vertical, 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 vertical. That looks clear. That's clear. And this looks clear. So he looks like he's safe there. This is great. Maybe we got our first solution. How about this one? Vertical, 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 vertical. Oh, this would be okay, except for the problem where it looks like we're going to get attacked there. What do you do now? Well, backtrack. Try this one. Can't go there. Can't go here. Backtrack. What about this one? Vertical. Can he do that? No, he can't do that. He's got a vertical attack there. How about this one? That's an angle. Backtrack again. Notice we're going back here. He's open a vertical attack. How about here? That one goes there. This one goes here. This one's safe. Okay, and we come back down again. Start at the left. Vertical attack. We're looking good there and there. This was an angle attack, vertical, vertical. Looks like an angle attack there. Vertical attack. What about this one? He's open at... Yep, now it's a failure. Again, we come back up here and try and reassess this one. Vertical, angle, angle, angle. This doesn't work. So we just keep on going back up. All right, now, how do we do this software-wise? All right, every single row that we just looked at did the exact same thing in the exact same order, and that is specifically put it in the first column. Ask, is it open to attack? Is it a safe queen? Is anything above it capable of attacking that queen? And if there isn't anything up there, or there is and it's not lined up to be able to make a move to attack it, it's safe. And then we go on to the next row. Every time we go to a next row, we do the exact same thing in the exact same order. Okay? That is, put a queen in the first column and ask, is it safe? No. Is it safe? No. Is it safe here? Yes. What do? We start a new column and we ask the same thing. We do the exact same algorithm. Is it safe? No. Is it safe? No. Safe? No. Safe? No. Safe? Yes. All right. So look at what's happening here. Each row we can implement as a recursive call to a function with a name like place queen. Place queen, and we give it a row number. Okay. That function simply has a loop that says for 0 through 7, put a queen on the board. Well, starting at 0, and then ask, is it safe? Write a subroutine called check safe or something like that, where you pass it the row and column number, and write some loops in there that check all rows greater than the row it's on, or rather, I should say all rows less than the row it's on, assuming this is row 0 up here. Less than the row that's given and greater than or equal to 0, and ask if there's a queen up there. If there is, then it's not safe to a vertical attack. Do the same thing for these angle ones, right? What are you going to do there? Well, you're going to write a loop, but it's going to iterate in both rows and columns at the same time. Now, you can simply, naively, you would simply say, check again all the rows and move over one on the column to the right to check this angle. And then you'd use the same naive line of thinking, maybe moving the column, subtracting one by the column, moving to the left as you go up. Well, obviously, you'd run off the board in this case. So when you write the loop that checks these angled situations, like if you do this one here, it's safe in both directions. But as you start moving over, it's safe to go up 2 rows on this angle, right? subtract 1 from row, subtract 1 from the column, subtract 1 from row, subtract 1 from the column. In order to find these elements in a two-dimensional array, you can only go up 1 row, or shall I say subtract 1 from the row and add 1 to the column to go in this direction once. Then once you subtract 1 from the row and add 1 to the column again, you're in column number 8, right? This column 0 through 7, this would be column index number 8. So just like checking to make sure the column is greater than -1 over here, you got to make sure it's less than 8 to make sure it doesn't go off this side. All right, so you got to just keep your wits about you. Don't run off the edge of the board while you're trying to check the above safety from above when you're going on this angle. All right, so there's two things to check. That's all I wanted to make clear on that. Okay, so you have a nice subroutine called check safety, and you have this recursive routine that simply has a loop in it that counts for I equals 0 through 7 maybe. Okay, and then call your check safety routine. It should return maybe a Boolean that's true if it's safe and false if it's not safe, right? So then it might say if not safe, go try the next one, right? Go try the next one. If it is safe, what it would do is it would recursively call itself and say place queen on whatever the row is for this iteration plus 1. So what are you going to do? You'll pass this subroutine row plus 1, whatever the row is this guy was doing. 1, 2. He was doing row number 2. He would call place a queen. He'd pass it the board and give it row plus 1, which would be number 3. Okay, so what does it do? That would execute a new instance, create a new stack frame, and a new instance of the place a queen function, and it would say for I equals 0 to 7, check the queen for this row and column. Check, 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 check. And if it's safe, recursively call again to row plus 1. It would start a loop from 0 to 7. Check, 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 check. Maybe it's safe here. I'm just saying. I don't want to go through all the details. Let's just assume these are all safe, right? Eventually, you're going along. You've got all these safe things. Let's say, okay, now this one's unsafe. It doesn't work. We've seen plenty of backtracking. What do you do, right? Well, if you end up on running off the right end of this row, for I equals 0 to 7, check and see if it's okay. Well, if this thing runs out, you saw it, you take it off the board, remove it from the data structure, set it back to false if it's a bunch of Booleans, and you simply return. And what are you returning into? Well, you're returning into the prior call in this recursive, nesting of place queen function calls to a loop that's already in progress. So in this scenario, assuming this was safe and correct, and obviously it's not, but let's assume it is, he would be in the middle of executing his iteration for index equals, column 2. He would just simply resume. Okay, column 3, column 4, column 5. Maybe he's safe over here in column 7. What does he do? Well, he calls place a queen on row 6, index number 6, 0 through 6. So it'll start a loop for 0 to whatever. Let's say it's safe here. What does he do? He recursively calls for row number 7, place a queen. Let's say it's safe there. This is interesting. Now what do we do? Who does he call? What does he do? Well, if he recursively calls place queen and he passes it row index number 8 down here, we know there is no 8. That would then be our base case in our recursive logic, okay? So in your place queens routine, you have the loop I've been talking about that calls the check safety for each column on any given row. And if it is safe, it recursively calls place queen again for the next row. But it also has the need to make sure that the row numbers are valid. The first line of code in your place a queen routine could simply ask, is the row number greater than 7? Well, if it is, then you know you're down here. And if you know you're down here, then you know that all of the checking of all these queens have returned true and that it is safe. Then this would represent, at that point in time, a solution out of the 92 possible of all these arrangements, okay? What do you do? So now it looks like this recursive function simply says, place queen. What do I do? Well, if row is greater than 7, then print out the board. This is solution number whatever. Keep a variable somewhere, maybe a global or something that says print, solution number 1, and just print out X's and dashes that match the Boolean values of a two-dimensional array that represents the board. Okay? When you're done printing out the board, there's absolutely nothing to do. Simply return. Well, remember, every single time you're in your main loop of iterating here, well, you're returning back into a loop in progress, all right? So what would you be returning into when you leave this row 8 guy that just dumps out the board as a solution? Well, you're going to go back into row number, the call for row number 7 here, whose current value here is what? 1, 2, 3, 4, 5. Okay, and he's in the middle of his loop, so he'll simply go on to the next one. Check the safety here. Maybe he gets over there and he finds out he's safe. Again, this isn't, but let's assume it is. For the second time he sees it, and he's going to recursively call down. We saw that up on the top. There were more than one place where a queen was safe, and we recurse down, and then it would come back up eventually, and so on, right? So this works in all the scenarios. It just so happens that if and only if you're on a row that's greater than 7, you can know that you found a solution, all right? Print it out, return. Well, once this row number 7 actually runs off the end, that loop is done. Does the same thing all the other loops do when they run out of columns. It returns to the previous row already in progress. Who would check some more? If he finds it, again, row 7 would start again. If he finds a good one, row 8, oh, I found another solution, print it out. This is how you're going to get all your solutions in this scenario, okay? So eventually, this will end up, whether it prints solutions or not, run off the end, as will that one, as will this one, and so on. So no matter what, we will have checked all the possible scenarios for these 3 rows down here, given a situation where the queens are all safe above, which was something, I think, like this. I don't know what it was, like that maybe. And when that's done, they've all returned. The lowest one that is not yet returned simply advances to the next column and checks again. In this case, that would be safe, right? He would come again. Maybe you'd find another safe one here, and so on. Maybe this is another solution. When this guy finds out he's safe down here, he would then call down, print out another one. Eventually, blah, 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 blah. He runs off the end. He's not safe anymore. He's run out. Same thing here. He runs out. Same thing here. He runs out. Maybe this one's there. He runs out, and he's already sitting there. Okay, I was safe, and I tried the next one. Oh, there isn't one, so he runs out of places. He moves to the next one here. You can see that's safe, and it continues again, right? So what will happen is eventually each one of these will have walked all the way over to the right, including the very top one. And all of the combinations below will have been assessed and printed out. You'll see the 92 possible solutions all printed out. And the last time through the recursive, expansion here will be when this top level row reaches 7, goes over to 8, and he's removed from the board, and he returns. Okay, where's he going to return to? Well, that's the last one. It'll go back to your main function, and you're done with your program. Okay, so what do we know? We know the base case is then, if you do it this way, the base case is you've been asked to do row number 8, and you know you have a solution. Print it out. All right. The other case, the non-base case, is to run a loop from 0 to 7, checking the safety. If it's safe, recursively call back in to check the next row. All right? That's how this thing works, the mechanics of the whole thing. So what else do we know? We can ask questions now and say, well, how many recursive calls can be going on at any one time? Well, we know that when main calls place a queen, there's a stack frame that represents the state of the queen to be placed on this first row, because main will call place queen for row number 1, and it'll pass it the board. Okay, that will call place queen for row number 2, which will call it for 3 and 4 and 5, 6, 7. The 8th row, okay, index 0 through 7, right? So what'll happen is place queen will call place queen for row 0 will call it for row 1, 2, 3, 4, 5, 6, and 7, who will also call it for row 8. So that's the total number of recursive nested calls that we can ever have in this program. In other words, it can never go hogwire. It can never go haywire, okay? It cannot run unbounded. This is a well-bounded problem. The most you'll ever have is the 8th one down here that prints out the board. When it is done, they return back up like this. So what's going to happen is these subroutine calls will nest down recursively up to 8 times. It'll do it 92 times. It'll hit the bottom row here because we know that there's 92 solutions have been mathematically proven. You can go ahead and look on Wikipedia and read all about it. Also, there will be plenty of nested recursive calls that don't make it to the bottom. We saw that. Like here's one right here, right? When we get down here, we start moving across and so on. When you get a situation like this, where all of a sudden we got to the right end, we didn't even get to the bottom and we couldn't find any place, for example, that'll go away. So it'll only come down part time sometimes, and then it'll go all the way other times, all right? The point is the number of nested calls is bound by the number of rows, because the row index number is the variable that you're passing back into the recursive call that's used to determine the base case. And when you do call recursively, you always add 1 to the row. So the total number of recursive calls will always be bound to 8. So I hope this high-level overview is useful. Thanks for watching. See you next time.